Okay, so today we're going to be talking about cardinality, and in particular, we're going to focus on the pigeonhole principle. And the readings for this that correspond to this are section 20.1 from Logic and Proof, and 13 and 14 from the Fundamentals of Higher Mathematics. Okay, so the first thing to know is our standard set of n elements. So for any natural number n, we're going to let n bar be the set of all natural numbers m such that m is less than n. And we've seen this now many times on the quizzes, but this is a definition in general. Okay, so now we're going to define what it means for a set to have n elements, which is just supposed to capture the intuition that I'm sure you already have. So if we consider a set S and a natural number n, we say that S has n elements if there is a bijection from S to n bar. So we say that S has n elements, or we can use some jargon and say that S has cardinality n. And we can write bar S bar equals n. So this thing here, bar S bar, we would read as the cardinality of n, or sorry, the cardinality of S. So this equation says that the cardinality of S is n. All right, and so if a set S has cardinality of some natural number, then we say it's finite. So if S has cardinality n for some natural number n, we say that S is finite. And if it doesn't have cardinality n for any natural number n, we say that S is infinite. And we'll talk in later lectures about different kinds of infinity, but not so much in this lecture. Okay, so the reason why this is the definition is, say you had, hopefully you have some good intuition about what a bijection is from the section on bijections, but just to go over that again, say you have some set S that consists of 3 elements, A, B, and C, and we of course want to say that that has 3 elements, because that's pretty clear. So we've got our standard set 3 bar that has also 3 elements like this. This is 3 bar. And the bijection from S to 3 bar is a function that sends each element in S, of course, to an element in 3 bar, but we never have a situation like this. So we never have that 2 elements are going to the same element. So each element in S has to go to a different element in 3 bar. And furthermore, we have to make sure that all the elements in 3 bar get hit by an element of S. So this forces a situation like this. So it forces that each element in S goes to exactly 1 element in 3 bar, and every element in 3 bar is paired with an element of S. So it's a bijection you can think of as a way to match up the elements of S with the elements of 3 bar, so that you can say that there's a 1-to-1 correspondence between them, so that they must have the same cardinality. And let me just point out that there are a whole bunch of bijections. This is one I've drawn here. But of course there's, let's say, this one, like this, and there are many more. So Even though there are many bijections, when we talk about cardinality, we don't care about all the different ones. If you want to say that S has cardinality 3, then you just have to exhibit 1, and that's good enough. Okay, so here are some useful facts about cardinality that hopefully seem very reasonable. So first of all, if we have two sets A and B, and then we take the product of them, and then we want to know what the cardinality of that is, then this is of course, so I don't know if it's so obvious, but hopefully it seems reasonable, that this would be the cardinality of A times the cardinality of B. And I encourage you to work out some very, very simple examples to check that that makes sense. And in general, if we take product of a whole bunch of sets like this, then we, if we're just interested in the cardinality, we take the cardinality of all the sets and product them up. So take the product of all of them. And if we take the union of two guys A and B, this is going to be the sum of the cardinalities, because of course we're putting A and B together, so it should kind of sum up the cardinalities. But then we have, oops, I don't know why I wrote S there. Then we have to make sure that we're not double counting elements that might be in the intersection of A and B. So if A and B have stuff in their intersection, then we've counted them twice, once in A and once in B. So we're going to subtract off one copy of that intersection. And so in particular, if A and B are disjoint, which means that their intersection is empty, they don't have an intersection, they don't overlap, then of course there's nothing in that last term, so we see that the union of A and B is just the sum of the elements in A and in B. And then we can also should write the cardinality up here. So we can also take the cardinality of a big union. If they're disjoint, then the formula is very simple. It's just the sum of the cardinalities of each guy. And here again, we need all of the AIs to be disjoint, and so we ask that they're pairwise disjoint, which means that if we take any two guys that aren't the same, so we take like A1 and A3 for example, and we look at the intersection, we want that to be empty. So we want that none of them are overlapping any other ones. So if that's the case, then the cardinality of the big union is a big sum of all the cardinalities. Okay, so now let's talk about the pigeonhole principle, which is really just a theorem. So it's not really a proof technique or anything, it's just a theorem that we're going to be using in various proofs. But the proofs do kind of follow the same pattern. There's kind of a trick to get used to in using the pigeonhole principle, so that's why it's one of our learning objectives. Okay, so the pigeonhole principle says the following. For any natural number n, there is no injection from n plus 1 to n, which hopefully seems reasonable. And let's think about what this is really saying in terms of pigeonholes. So the idea is that if we try to put n plus 1 pigeons into n pigeonholes, then at least one pigeonhole, will have more than one pigeon. Oops. So let's think about this in terms of pigeons and functions. So say we've got our set of pigeons here. We've got a bunch of pigeons in our set. Oops. Pigeons. And we've got a set of pigeonholes. Maybe they could even draw them a bit more like pigeonholes. So we've got here a set of pigeonholes. If we try to construct a function from the set of pigeons to the set of pigeonholes, so we send this guy to that hole and this guy to that hole, and I won't try to draw them all because it'll be hard to read. But if we try to construct a function that sends each pigeon to a specific pigeonhole, and if we have one more pigeon than pigeonholes, then of course one of the holes will have more than one pigeon in them. Okay, so that's the pigeonhole principle. And there's something also called the generalized pigeonhole principle, whose statement is a bit more complicated, but the idea is not much more complicated. So the generalized pigeonhole principle says the following. If we have 3 natural numbers and L is bigger than m times n, and if we have a function f from L bar to n bar, then the pre-image of one of the guys in the codomain, so of some element y in n bar, must have more than m elements. So let's think about the idea. And this is just maybe clear how it's generalization if you think about pigeons. So if we try to put L pigeons for this L greater than m times n into n pigeonholes, then at least one pigeonhole will have more than m pigeons. So if we have a set of our pigeons, many pigeons, and we have, again, a bunch of pigeonholes, and here there are L greater than mn pigeons, and here we have n pigeonholes. And if we try to assign each pigeon to a hole, then there's going to be one hole, say this one hole that has more than m pigeons assigned to it. And the reason why this mathematical statement is talking about the pre-image is because if we're looking at this hole, then this hole, this guy here, is going to be our y. And the pre-image are all the pigeons that are being sent to that y, right? So the pre-image here would consist of these 3 points. So this would be f inverse of y. Okay, so when we look at the pre-image of this y, we'll expect to have more than m pigeons. Or let's say there's some y here in the codomain, there's some y over here, there's some element of the codomain whose pre-image, when we look back at the pigeons, looking at all those pigeons that are sent into that hole, we should see more than m pigeons for one of those elements. Okay, so hopefully that seems also very reasonable. Now let's look at an example. So we're going to consider a prime p. So this example is extremely important fundamental theorem in number theory, which has many, many applications, all sorts of practical stuff. So if it weren't for the pigeonhole principle, then nothing would really work out. Okay, so we're going to consider a prime p and a natural number n that's not divisible by p. Okay, so p is not a factor of n. So I claim that there exists a natural number that I'm going to call an inverse of n, which is a multiplicative inverse of n. So if I multiply n and n inverse together, I'm going to get 1, but this is mod p. Okay, so in particular, every number that's not equivalent to 0, mod p, has a multiplicative inverse. And like I said, this is very important theorem that makes the whole world go round. Okay, so how are we going to prove this? We're going to suppose that this is not true and try to derive a contradiction. So we're going to consider the set of multiples of n. Oops. So we're going to consider the set of multiples. What have I written here? Something ridiculous. Okay. Consider the set of multiples of n such that 1 is less than this number a, which is less than or equal to p minus 1. So we can kind of write this more clearly or more intuitively like this. So it's n, 2n, 3n, dot, 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 p minus 1, n. Okay, so you might ask yourself, why are we doing this? Well, it's of course because we want to show that one of these guys here, one of these an's, is 1, right? We're going to show that one of the a's is the inverse of n. And it maybe takes a bit more intuition of modular arithmetic than that might be like extremely apparent to you at this point in the class. But these are all the multiples that matter mod p. If we looked at pn, that's equivalent to 0, so that doesn't matter. And if we looked at p plus 1n, that's equivalent to n, so we kind of go back around in a circle. And if we look at p plus 2n, that's equivalent to 2n, etc., etc. So these are all the multiples that matter mod p, in the sense that all the rest of the multiples are equivalent to one of these ones that we've already written down. Okay, so we're going to try to show that one of these a's is the inverse of n. So what we want to say first is that none of these are divisible by p, of course, because p doesn't divide n, and we're just looking at an, where a is between 1 and p minus 1. So of course p doesn't divide any of the a's. So none of these guys are going to be equivalent to 0 mod p. And we're also going to say that none are equivalent to 1. So none can be equivalent to 1 mod p. This is basically our assumption when we said suppose not. And this is because then an would be equivalent to 1 mod p for some natural number n, which would then be the inverse. A would be the guy that we're looking for. And we are supposing that there is no inverse. Okay, so we know that none of these multiples can be equivalent to 1. None of them can be equivalent to 0. So there are only p minus 2 equivalence classes left that these multiples could be in, right? Because there are p equivalence classes, because there's the equivalence class of 0, of 1, of 2, dot, 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 of p minus 1. Those are the equivalence classes. And our multiples can't be in the equivalence class of 0 or of 1. So we have p minus 2 equivalence classes left and p minus 1 multiples to think about. And now we can use the pigeonhole principle, because each multiple must be in some equivalence class, but there are more multiples than equivalence classes. So 2 multiples must be in the same equivalence class. So by the pigeonhole principle, 2 multiples, let's call them an and bn, are going to be in the same equivalence class. Then they are, of course, equivalent. That's what it means to be in the same equivalence class. So we have this equation, and then we can just rearrange everything, do a little bit of arithmetic, and we find this. And again, let's remember that n, this factor here, n, is not divisible by p by hypothesis. And since a and b are between 1 and p minus 1, a minus b also can't be divisible by p unless it's actually 0. So then we must find that a minus b, so if this fact that this guy is equivalent to 0 means that this whole thing must be divisible by p, which can only happen if a minus b is 0, or in other words, a equals b. So this can't happen, basically, because we're saying that 2, by the pigeonhole principle here, 2 different multiples, maybe I could have used the word different to be really clear, 2 different multiples must be in the same equivalence class, but then we show that they're the same multiple here, so we're contradicting the pigeonhole principle. And this is a contradiction, so then we can say that our original assumption that we suppose that what we were trying to prove wasn't true must be wrong, and so what we're trying to prove must be true, which is what we wanted.